Hey guys, I'm sure if you're like me, you're looking forward to the end of the year. You're thinking about what that sweet, sweet time at home would be like. Is it too soon to make jokes? Probably. Okay. We got two little sections left. We're gonna kind of use some really basic ones out of these two little sections, kind of discussing what these things look like and how they kind of fit together. We're not going to go too in depth in these sections because these are going to be the last two sections we do. We're going to be doing 6.1 and 6.3. Hopefully, both videos will be posted by the end of Tuesday, today. And both homework assignments should be pretty short, despite looking a little longer than some that we've had. They're pretty quick to do because a lot of them are not asking you to go too in depth into this. I'm trying to make your final as nice as I can, and using the information we have on these last two sections to kind of write a quick final using the information. So, the last two things we're going to talk about are exponential and logarithmic functions. Now, let's start off with what's the definition of an exponential function. Well, here we go. Exponential functions are any functions of the following form. f of x is equal to a times b to the x power. In this case, it's important to note this is different from other functions we've had. So in other functions, we've dealt with powers before, but we've dealt with the variable being in the base of the power. So in this case, this is what we call a parabola. And if you have something like x cubed, this is something like a cubic. And even when you had like square root functions, these are all powers though, where you have x, your variable, to a power. This function is a little bit different, and it acts different because of that. The variable in this case is actually in the power, meaning your power is what's changing over time. So just real quick, I want to look at a very brief example, kind of showing what this looks like, using a number. So I'm going to pick a kind of a random number. In this case, I'm going to pick the number 3. So in this case, I'm going to use the function 3 to the x power. And I want to showcase what this looks like when we choose different x's. So make a full list here. So let's talk about first what happens if x is 1. Well, if x is 1, that means we have 3 to the first power, which of course is just 3. If x is 2, notice that my function changes. I would have 3 to the second power, and 3 to the second power means 3 squared, or 3 times 3, which is 9. If I have something like a 3 that I plug in, this would mean 3 to the third power, which means I would do the number 3 repeated 3 times, which is, of course, 27. If I was to do something like 4, I have 3 to the fourth power as my x, which means I'd have the number 3 appearing 4 times, which is, of course, 81. And so you can see that if I plug in 1, my answer is 3. If I plug in 2, my answer is 9. If I plug in 3, my answer is 27. If I plug in 4, my answer is 81. Notice these numbers are shifting rapidly upwards. This is referred to as exponential growth, because the number is going up very quickly. I had 3, then I had 9, that's not too big a jump, but then I jumped to 27, and then I jumped all the way up to 81. And in fact, if you go up to the next one, it gets even bigger. So if you go to plug in 5, this is equivalent to 3 to the fifth power. That'd be the number 3 multiplied 5 times, which number 3 multiplied 5 times is 243. And if you did it 6 times, 3 to the 6th would just mean that we multiply the number 3 6 times, 5, 6, which is 721. So you can see in a very short period of time, just from the values of 1 to the value of 6, we've gone from 3 to 721. That is a huge jump in a very short period of time. And so this is referred to as exponential growth, or an exponential function. Exponential meaning that it grows or decreases rapidly. Now, this nice little thing about this table is that we can actually continue in both directions. Because it is a function, we can plug in whole values. We can also plug in fractional values, which I'll talk about in a second. We can also plug in negative values. So we can plug in like -1, -2, and -3. So if you plug in if you plug in 0, it ends up being 1. Because you have 3 to the 0 power. And we talked back in chapter 2 how anything to the 0 power is 1. If you plug in -1, this is 3 to the negative first power, and I'm going to skip my math here. This is equivalent to 1/3. To the negative second, this would be, well, 3 to the negative second power, which is 1/9. And then 3 to the negative third, which would be 1/27. Okay, so let's take a look at this row of numbers we have here and talk about what we can notice as a pattern. First thing to note about 3 to the x power. First of all, our solutions are always positive. Which is neat, right? When we plugged in -3, we got a fraction, but it's a positive fraction. We plug in 0, we got a number, but it's a positive number. Plug in 4, we get a number, it's a positive number. No matter what number you plug in, the solution will always be positive, provided a is greater than 0. Remember, this a is coming from this equation. So if a is bigger than 0, your numbers are always going to be positive. And if a is less than 0, it's always negative. Next thing to notice, in this function, if we're looking at just 3 to the x, you notice that it increases rapidly from 1 up to 721 in a very short period of time. So here's the thing. If b is bigger than 1, this is referred to as exponential growth. If b is less than 1, but still has to be bigger than 0 for this to work, we call this exponential decay. Now note in this case, b is the number that x is attached to. The x is not being applied to the 2 at all, or to the a at all. So an example of an exponential function that we could have might be something like 6 times 3 to the x power. This is considered to be an exponential function. Why is it considered to be an exponential function? Because it matches our form. In this case, 6 has a name. It's referred to as the initial value. And so if a problem ever asks what the initial value is, it just means what's the number in front of our powered. The 3 in the x, the 3 is referred to as our base. And so if the question asks what the initial value is, it's the number that's in front of your exponential. And if it asks what the base is, it's the number inside your exponential. Now, what happens on top can be simple like x, but it can also be a function. And it still be considered exponential. So a second example that's more complex but has the same rules would be like -2 times 1/2 to the -6x minus 1 power. So in this case, my initial value would be -2. My base would be 1/2. And my power, in this case, is an expression. And that's fine. You can have an expression as a power, and that's totally fine. It's going to look and act very similar to this one, but not exactly the same. And so all two of these are, in fact, an exponential function. So make sure a lot of your questions tonight ask you to be able to evaluate things like, what's the initial value, what's the base? Well, this is the most basic part of it, defining it as it is. Now, in this example, because my base is bigger than 1, we would say this is exponential growth. In this case, because my base is less than 1, we would say this is exponential decay. Now let's take a look at what these two things look like in terms of a graph, because graphs are really helpful to visualize some of these things. So I got my little TI calculator. If you're using RabbitEmu, yours might look something like mine. If you're using something else, it'll look pretty similar. I'm going to type my function. Let's showcase where some of these pieces are in the calculator. For this calculator, this little arrow key is how you do powers, in case you were unaware. So if I type in this first function, it is 6 times 3 to the x power. Well, let's take a look at what this looks like. You can see, if you look at this graph, how it's positive. Even though it does get very close to the axis, it always stays above the axis. And then over time, it does in fact go up. You can see from my list of my table here that it goes up very quickly. After just 10 is plugged in, we are in the 300,000s. So it's rapidly increasing. So it starts off very, very small. So my left-hand end behavior would be very small, close to 0. My right-hand end behavior would be going towards infinity. On the other hand, let's see if I put in my other function, which will now be here in red. This one's a little more complicated, so I'm going to do 2 times 1/2 to the 6x minus 1. And we got this one. What you'll notice is, as this thing graphs, because that number is negative, we have a negative 2 here. Because it is negative, that tells me that the answer is always negative, but the question is, how far negative? Is it really negative, like negative 1,000,000? Or is it close to 0, like negative 1 or negative 0.2? And so because my number in front is negative, my initial value being negative, tells me that my answers are always negative. Next we can see in this picture, notice how it starts really negative, like off the screen really negative. In fact, the first number we have at 0 is negative 4. But if we go up in our table, you can see if we go to like negative 3 or negative 4, how quickly this gets to be incredibly negative. Like negative 16,000, this is negative 100,000, that little e tells you it's 6 zeros. This is negative 6 million. And so this one, because we have a 1/2 in my equation, in my base, notice how it starts very negative, and then quickly becomes very, very tiny, but still negative. And so it still matches all of our rules, right? It's always negative because the number in front is negative, and it's decay because over time it is getting smaller. So as we look at our graph here, we can see that over time it is in fact getting smaller and smaller, closer and closer to 0. In this case, smaller means close to 0. And so this represents exponential functions. These are functions that have this property, that always act this way. And note the difference between this and the previous functions we've talked about. Previous functions follow different patterns, right? They either went to infinity or they went to negative infinity. They did something. Whereas exponentials, they can go to infinity, like this first one here in blue, or they can just go to 0, like this red one. And so it depends on what your initial value is, whether it be a positive value or a negative value, and it depends on what your base is, whether it be one bigger than 1 or smaller than 1. Now, before I continue, I do want to note, as some of you guys might be wondering, what happens to the graph? Like, why does it have to be bigger than 1, or bigger than 0? Like, why does this have to be the case? Why must our b be positive? So let's take a look. If you try to type this in and say, make our base, so I'm going to have what the front number is, let's say it's like a 2, and then I'm going to take 2 times, I'm going to make this negative 3 to the x power. This function does not graph well, and it really doesn't like to even evaluate it. So let's take a look at our graph. So in this example, right, our initial value is a value of 2. Our base is a base of negative 3, and I want you to notice something about the graph. It doesn't graph. That is because negative powers do not follow the same rules. Negative bases break down a lot of the rules. You notice that in my table, how I'm getting answers, but if I actually look closer at my table and try to plug in, like, let's say instead of doing it in the table, we try to evaluate, it was 2 times negative 3. What if I did it to a half power? It's like a fraction. What happens? Nothing. It ends up being imaginary. And so what this is saying is, when we try to graph this, it ends up becoming an imaginary graph, and that's why the graph doesn't go. It's because some answers are imaginary, so the graph ends up being imaginary for some of its parts. In fact, most of it is imaginary. And so in this example, like, you have to have a base that is between 0 and 1. So bases of 3 are good, bases of a half are good. Your initial value can be anything, though. So it can be positive value or it can be negative value, but depending on which one it is, will indicate whether your graph is always going to give positive answers or always going to give negative answers. If your A is positive, you'll have positive answers. If your A is negative, you'll have negative answers. Okay. Next thing. In your textbook, I'm going to notice a couple things here. I'm going to do the triads this time, see if we can do something a little different. This is an example of one where I have 4 different examples. 2 of these are considered to be exponential functions, and 2 are not. This first one, f of x, is not. This first one, f of x, is very much not, because my x is not in the power, it's in the base. G is. And g is considered to be a decaying function because 0.875 is less than 1. So this is considered a decaying function. H is not, because again, there's no power. Your x has to be in the power. J is, because it's in the power. And in this case, because my base is positive, this would be a growth function. Okay. How do you evaluate these? Well, the nice thing is, a lot of the problems that you have tonight to ask you to evaluate are simple plug and chug. And so, let's take a look at some problems. As you can see, we're skipping some of the section because, well, it's the last week, and I want to make sure you guys have a good last week. Notice that your first few questions, 9 through 17. 9 gives you an equation, asks you questions like, which is growing faster, or which is growing slower. It asks you questions like, hey, what's going to happen after 20 years, or what's going to happen after 100 years? And these kinds of questions just mean to take 20 and plug them in. It means to take 100 and plug it in. So let's talk about how to do that. So in this case, we're going to do number 11 here together. We're going to do our first few problems together here. I think it's a good use of our time. So let's take a look at our first problem. 11. So it says, for the following exercise, consider this scenario. For each year, t, the population of a forest of trees is represented by the function a of t is equal to 115, parentheses 1025t. In a neighboring forest, the population of the same type of tree is represented by the function b of t equals 82, 1.029t. And these have been rounded. So part 9. Nine asks the question, which of these is growing at a faster rate? Well, in this case, faster just means larger base. And by extension, slower would mean smaller base. So if I'm going to write down some things for my notes, a good thing to put in here are some real-world examples. So some terms. If it asks which one's going faster or slower, faster just means larger base. Slower means smaller base. Now, these can still both be positive, it's just which one's the larger positive number or the smaller positive number. They could both be negative, so which one's the larger negative number or the smaller negative number. So number 9, let's take a look at our two formulas. Our two formulas are 115, parentheses, 1.025 to the t power. That's my A. My B is 82, 1.029 to the t power. So to answer number 9, the question is which of these has the larger base? Remember, my base is a number inside, and so this one has the larger base. Not by much, of course, but it is larger. Therefore, this one is the one that is growing faster. Now, number 11 says, what do you think will happen after 20 years? Oh, I guess we could do number 10 as well. Let's look at number 10. Ten asks the question, which forest had a greater number of trees initially? So that's asking about the initial value. Now, my initial value comes from the number up front. So A of t has an initial value, we're going to be IV of 115. B of t has an initial value of 82. So this example, so B of t is growing faster, but A of t has a larger starting value. Again, this is a number of the questions they ask you to interpret what you're reading. And so it's really important to be able to see that kind of difference. Now let's ask about number 11. Number 11 and number 12 are both really similar, so if you can do number 11, you can do number 12. Number 11 asks, assume the population models continue, which forest will have the greatest number of trees after 20 years? What this means is, what happens after 20 years of time to each of these formulas? So for number 11, it's really asking us to simply insert into this function the number 20. So for this first one, I have 115 times 1.025 to the t power, so we to the 20th power. For the second function, I have 82, 1.029 to the 20. Now the instructions do say to make sure to round to the nearest whole number. So now I'm going to open up my calculator and type these two things in. Okay, so the first one says 115 times 1.025 to the 20th power. So now exponential growth just means that it grows quickly over time, but it quickly is relative. This number, 1.025, is very, very much near the number 1. And remember, 1 is the breaking point, the big difference point between growth and decay. So the closer you are to 1, the less explosive your growth is going to be. Like if your base is 20 or 30 or 50, you're growing very fast. If your base is 2, you're going to go a lot slower, but you are going to grow quickly by comparison to anything else. So let's plug these in. At 115 times 1.025 to the 20th power. This tells me after 20 years, there'll be 188 trees. Let's try the other one. So take 82 times 1.029 to the 20th power. And it tells me that after 20 years, there'll be 145 trees. So in forest A, there'll be 188. In forest B, there'll be 145. Make sure we answer a question. By how many? So which one has the largest? Well, this one has the largest, so A is largest. By how many? Well, this one has 188. This one has 108 and 145. So we can answer that question by subtraction. By 188 minus 145 is 43. So there's our answer. Number 11 asks which one is the largest after 20 years. A is the largest by 43 trees. Number 12 asks about, what happens after 100 years. And here's the thing. B is growing faster. So there's going to come a point where these two end up being the same. And there'll eventually become a point where B ends up being the larger one. And that's what 13 is asking about. But notice how most of your work today and what your final one is going to consist of is comprehension of what the heck this formula literally means. Given a formula, can you identify what the initial value is? Can you interpret whether it's going to be growth or decay? Those kinds of basic questions. I'm not looking to go too deep into these sections, so we're just looking for basics. Now, on the other hand, there is one more thing I need to tell you. In some of your problems, you will notice a little letter E. So if you look right here on 46, which is one of the problems you have, 47 and 49 all have this little letter E. E is referred to as the exponential number. The farther you go in mathematics, the more E really, really is important. E, if you have a calculator with you, is known as Euler's number. E is defined very specifically, and it's usually saved on your calculator. For mine, my E is actually right here. It's in blue, a little tiny one. And you hit the second button, and then you can see how it's got E. So there it puts E into the equation. E, in this case, is not a letter. E is like pi. E is representative of another number. E is, in fact, 2.717, I do believe. It's actually in your book. I'll go to that real quick. And so if you have no other options, you can just manually plug in E. It's kind of a pain. But in most cases, you'd rather use the number E, 2.718. And it's just like pi, and then it keeps going, and it's defined by something else. And so if your problem asks you to do something like these ones where it says, evaluate the function, what it just means is you need to plug -1 into this formula. So for example, if I was to do number 46, where it says find f of 3, what it means is type in e to the third power. Everywhere there's an x, remember, we're just going to plug in 3, and that will give you a number answer. That number is the one I'm looking for. So as you can see from most of your homework assignment, there's not a whole lot of components that are really crazy in here. In fact, the craziest part might be the ending ones, but you'll notice the ending ones all involve the same basic formulas. The only formula we haven't discussed yet is one specific real-world application formula that there's actually 2 different versions of in your book. It's this one. This will be your last piece of notes, and these are referred to as the compound interest formulas. Now there's 2 of them. The first one is for number n. The second one is for continuous. Depending on the problem you have tonight, you need to notice which one is which, and they'll always try to tell you. So, in this case, the formulas are, for this first one, a of t is equal to capital P times 1 plus r over n to the nt power. Now, in this case, P is your principal. It's also your initial value, so don't forget that. R is your rate, and make sure this is a decimal. That's a big detail. In fact, you might want to consider looking at example 8 as a good guide for these problems. And N is the number of periods. So it says it's going to do it daily. Days would be 365. And so if it said weekly, you'd do 52, because there's 52 weeks in a year. And so this formula is a lot of plug and chug. That's the only real application tonight that's really any difficult. I would strongly suggest looking at example 8 to assist with this in the text. It is on page 472. /490. The continuous one is a little bit farther down. It's often referred to as PERT. A of t, P e to the RT, in this case, everything stands for the same thing, so P is the principal, so it's the initial value, R is the rate as a decimal, and T is time. And so your last couple questions, that's 61 through 67, these ones, these involve these 2 formulas a lot. And again, I would strongly suggest looking at example 8 and looking at example 11. There should not be too many. There'll be one of these on your test for your final, but the main part of your final will consist of questions about, can you plug in, can you evaluate ones like 9 through 11. So this is your second to last assignment for the year. 6.1, exponential functions, on page 476. The big thing about it is making sure to understand what an exponential function is and how to use it with a calculator especially is really helpful. Otherwise, that's going to be it for today. I will post a second video tonight as well, just so that you have both, so those that wish can go ahead and get their stuff done. That way they can enjoy their time out. And those that don't, you will have the rest of the week in order to get your stuff finished. So that'll be it. Enjoy the rest of your day. Night.